Hey, welcome to Maths with EJD. In this video, I'll be talking about assignment problems and Hungarian method for solving them. So let's look at the assignment problem first of all. We've been dealing with all kinds of problems lately. We dealt with transportation problem, transshipment problem, and then now we are here talking about assignment problem. So what does that actually mean? The assignment problem, the assignment problem involves, it involves assigning n workers to n tasks, to n tasks or jobs in such a way, in such a way that each worker, each worker is assigned exactly one task. And each task is assigned, each task is assigned, each task, and each task is assigned, each task is assigned to exactly one worker, to exactly one worker. So it's some kind of one-to-one mapping of tasks and workers. So the goal is to minimize, the goal is to minimize the total cost. Want to minimize the total cost or maximize the total profit associated associated with the assignments. So basically, you want to assign one thing to the other in such a way that you spend the least amount of money or you spend the least amount of time or whatever else you want to minimize or maximize. So it should also be known that each worker to task combination, each worker to task combination has a cost, has a cost, or if you like, a profit. And we are trying to find the optimal assignment, the optimal assignment of workers to tasks to the optimal assignment of workers to tasks that minimizes the total cost, that minimizes the total cost. Okay. All right, let's talk about the Hungarian method. The Hungarian, I think this is a well-known method for solving assignment problem, the Hungarian method. So the Hungarian method, the Hungarian method is an algorithm, is an algorithm used to solve the assignment problem efficiently, used to solve the assignment problem efficiently. So it operates in the following steps. Okay, so let's talk about step one. For step one, you have um step one for Hungarian method, you subtract the row minimum. Subtract the row minimum. That's the first thing you do. So whatever you are considering, whether the cost or distance or things like that, they are presented in a kind of matrix form. So the first thing you're going to do is to subtract. You are going to do some row operations, which involves, first of all, subtracting the row minimum from each element in each row. So subtract the row minimum. So that means that for each column, for each row rather, for each row of the matrix, whether it is cost matrix, distance matrix, or whatever, for each row of the matrix, subtract, subtract the smallest entry. Subtract the smallest entry of that row from every element in the row. From every element in that row. First, that's the first step. Second step is so for step two now, you subtract, so you do that for row, right? Then you do the same for column. So subtract the column minimum, subtract the column minimum. Okay. So here now you say for each column of the matrix, for each column of the matrix, subtract the smallest entry, subtract the smallest entry of that column from every element, from every element in that column. Okay. Now, for step three, so having done the subtracted the row and column minima, so step three is such that you cover all zeros, cover all zeros with a minimum number, with a minimum number of horizontal and vertical lines, with a minimum number of horizontal and vertical lines. So minimum is key here. So if you can cover all the zeros with 3 lines, you shouldn't use 4 lines. That's the key thing. So you should only use 3 lines if you can't use less than that. Okay. Cover all zeros with a minimum number of horizontal and vertical lines. So here you cover each zero, you cover each zero in the matrix, each zero in the matrix with a line, with a line. So you use the minimum number, use the minimum number of horizontal, and vertical lines to cover all the zeros, all the zeros. That's step three. Then at step four now, you check for optimality. So step four, you check optimality. Check optimality. When do you know if what you have is now optimal? So here you say if the minimum number of lines, if the minimum number of lines is equal to the number of rows, to the number of rows or columns. Of course, you expect it's the same number of rows is equal to number of columns because you must have equal task and equal workers. So if the minimum number of lines is equal to the number of rows or columns, okay, in that case, an optimal assignment can be made by selecting zeros that are not covered, that are not covered. An optimal assignment can be made by selecting zeros in the matrix that are not covered by any lines. This is somehow. An optimal assignment can be made by selecting zeros that are not covered by any lines. Okay, I mean, when we get to the implementation, I'll explain what that should mean. If not, if not, you proceed. So if you have not got, or if the minimum number of lines is still less than the number of rows or columns, then you have to still proceed. So if not, step proceed to step 5. Okay. Then the last step is to modify the matrix. Step 5, you modify the matrix. Modify the matrix. So modify the matrix. So here, what you do is you find the smallest uncovered. That's if you have not reached optimal solution. So you find the smallest uncovered number, uh, smallest uncovered number in the matrix. Okay. And then you subtract it from all, you subtract that smallest number from all uncovered elements, subtract it from all uncovered elements, then, and you add it to the elements, covered by 2 lines. Add it to the elements covered by 2 lines. Then once you do that, you can return to step 3. So then return to step 3. Okay. So that's what the Hungarian method looks like. Let's take an example to drive the point home. So we have example now. So not too much stories. I'll just give the highlights and I'll show the table and we get to work. So imagine you have a situation where you have 4 workers. There are 4 workers and there are 4 tasks. 4 workers, 4 tasks. And then you have a cost matrix, cost matrix as given below. So you have worker 1, worker 2, worker 3, and worker 4. And then you have task 1, task 2, task 3, and task 4. Okay. So in the form of this matrix now, you have 23, 19, 18, 33. Then you have 16. So that's what all these cost simply means that if worker 1 is taking task 1, it will cost $23 or 23 whatever. So worker 1 task 2 costs $19. Worker 1 task 3 costs $18. Worker 1 doing task 4 costs $33. So it's more like you're making people submit some kind of bid or so. So for worker 2 now and task 1, 16, worker 2, task 2, you have 32, 24, 29. Then worker 3, task 1, 17. Worker 3, task 2, 12. Then this is 20, this is 23. And in the last row, you have 21, 20, 27, and 17. So, of course, the aim is to want to find find the best assignment, find the best assignment of task to workers that minimizes costs, that minimizes costs, minimizes cost. So that's what we are in for. So let's go for that. So let's just go ahead and use the Hungarian method as we have explained. So going by the Hungarian method, right? So you have so I'll just do it step by step. You have 23, you have 19, you have 18, you have 33, you have 16, you have 32, 24, 29, you have 17, 12, 20, 23, and then you have 21, 20, 27, and 17. Okay, we have all this, right? So the first step is to, what do? You do minimum row, minimum, okay, rather, not minimum row minimum. So you look for the minimum of each row and you subtract it from every element in that row. So we say row minimum subtraction. That's the first thing. Row minimum subtraction. That's the first step. So what does that give us? We have, so we go row by row. In row one, this is row one. So the minimum in row one is actually 18. So in row two, the minimum is 16. In row three, the minimum is 12. In row four, the minimum is 17. So in each of those rows, you subtract those minima from each element in their rows. So let's go for that. So here we have, so subtract 18 from every element here. Subtract 18 from every element. So we have 23 minus 18, that is 5. 19 minus 18, that's 1. 18 minus 18 is 0. 33 minus 18 is 15. The next one, we have the minimum value is 16. So subtract 16 from all of that. So 16 minus 16 is 0. Then you have 32 minus 16 is 16. 24 minus 16 is 8. 29 minus 16 is 13. Then again, you have the minimum in the third row is 12. So subtract 12 from each one. So 17 minus 12 is 5. 12 minus 12 is 0. 20 minus 12, that is 8. Then lastly, you have 23 minus 12, that is 11. Then in the last row, the smallest number is 17. So 21 minus 17 and all that. 21 minus 17 is 4. 20 minus 17 is 3. 27 minus 17 is 10. 17 minus 17 is 0. Okay, so this is what we have now. So that is first step, row minimum subtraction. Now, before you will do anything else, so you go to the second step where you do column minimum. That's step 2. Column minimum subtraction. Column minimum subtraction. So what you did for each row, you're now going to do for each column. So column minimum subtraction. So that is going to lead us to this now. So in each column, let's see which number is the smallest. So interestingly, in each column, the minimum is 0, interestingly. So nothing changes. Okay. So every column has a 0. So so it means we're just going to have the same thing, because we're just going to have now you're going to have 5 minus 0, 0 minus 0, 5 minus 0, 4 minus 0. And then you also have that all through. So so again, we just have the same thing, exactly the same thing. So 5, 0, 5, 4, then 1, 16, 0, 3, then 0, 8, 8, 10, and then we have 15, 13, 11, 0, because every column has 0 as minimum. So we just repeat what we have. So that is step 2. Now, step 3 now is to, let's see what step 3 says again. Step 3 says to cover all zeros with a minimum number of horizontal and vertical lines. Okay. So the next step, which is step 3, is to cover zeros. Okay. I want to cover zeros. That means for what we have, that's 5054, 11603, then 08810, and 15 13 11 0. All this. So you cover all the zeros with minimum number of lines. So here, no matter how hard we try, you can either cover, so you can cross horizontally or vertically. But no matter how hard you try, you can either do 1, 2, 3, 4, covering all the 4 zeros vertically, or you cross horizontally, 1, 2, 3, 4. So either way you go, you see that the number of lines are exactly equal to the number of rows, okay, and columns. So in this case, we can say we have reached an optimal solution because you have in every column there's a zero you can pick, right? So so let's talk about this step now. Step This is step 3, and we can check for optimality. This is okay. Step 4 now, talk about optimality check. Optimality check. Okay. So you see that no matter whatever you do, you cannot have less than 4 lines to cover the zeros. Okay. Um, in that case now, so you just say, since the minimum number of lines, since the minimum number of lines covering zeros, which is 4, right, is equal to the number of rows and columns, to the number of rows and columns. Okay. Then we have reached an optimal solution. We have reached, or better still, we have reached optimal solution. We have reached optimal solution. And it's particularly good that you have 1 0 in each column or in each row, anyhow you look at it. So finally, you can just talk about that. So you now have that representation now that you have 5054, then you have 11603, 11603, and then you have 0883, 08810, and finally 15 13 11 0. Okay, so this is worker 1, worker 2, worker 3, worker 4, task 1, task 2, task 3, task 4. And we know that we have reached optimal solution. So what you're just going to do, anywhere you see 0 now, check that what you see. Anywhere you see 0, those are indicators of your of the assignment. So we can just say, therefore, uh, can I call that step 5? Step 5, you have the optimal solution. Optimal solution. What is the optimal solution? It means that you assign worker 1 to assign task 3 to worker 1. So worker 1 takes task 3. Then if you look at the original table, that's where we had the cost. So worker 1 takes task 3. So, and what was the cost in the beginning? Worker 1 taking task 3 will cost $18. Okay. So cost $18 or whatever, maybe $18,000, anything you want that to be. So worker 1 takes task 3, $18. Then the next thing is that worker 2 takes task 1. So task 1 is assigned to worker 2. So worker 2 takes task 1. And if worker 2 takes task 1, the cost is 16. Oh, sorry, in the beginning, right? The cost is $16. Okay. So that is $16. Then the next assignment is that worker three takes task two. Worker three takes task two. So worker three takes task two. And what is the cost of that? Worker three, worker three, task two. That is $12. So that's $12. And of course, worker four takes task four. That is $17. Like that. So worker three takes task two for $12 and worker four takes task four for $17. Okay. So this is the optimal assignment. And what is the total cost now? Total cost is just the addition of all those costs. So that'll just be 18 plus 34, that's 18 plus 16, that's 34. 34 plus 34 plus 12, that is 46. Then 46 plus 17, that is 63. So it means that the total cost is $63. Is $63. Okay. So that if you do very well, you'll pay $63. You won't pay more than that. That's the minimum you can go. So that's the idea of the assignment problem. So worker one task, we take task three, worker two, task one, worker three, task two, worker four, task four, with the associated cost, and we end up getting $63. So that's how that has been for this particular problem. So if you have not subscribed to this channel, be sure to do that right away. Hit the notification bell so you can always get alerted each time a new video is released. Then comment, let me know if you want me to solve a problem or answer a question or teach a topic. Then like and share so that more people can have access to all this great learning. Till I come your way again, keep optimizing. Of course, watch out for the next video, which is going to be on a project assignment problem. And the last problem under the last video under Hungarian method will be about matchmaking, because marriage, like monogamous marriage, is more like a one-to-one assignment problem. So we're going to look at that kind of situation. So watch out. Bye.